Good afternoon, Math 105 students. So we have arrived this week at our last topic of our second act of the course. Our second act of the course is one in which we've been figuring out how to use the tools of algebra, the kind of algebra that you learned coming up through high school, to really be able to model and understand measured quantities, behaviors, and relationships that we see in our life around us. So that includes financial examples, it includes other examples maybe from polling in politics, other examples from the workforce, or you might be measuring sales data and that kind of stuff. We've been looking at how to use algebra to gain some insight and make some predictions in those various arenas. And so this week is about sort of putting the cherry on that sundae. What we're doing this week is looking at one more different kind of algebraic model. Besides the linear models that we started with in the first half of this unit, we want to figure out how to take what we learned last week about how to communicate about percentage and percentage change, and how to plug that kind of arithmetic into an algebraic model that can help us make predictions about how a quantity which might be consistently changing in a percentage fashion rather than in an amount fashion will behave into the future. So the typical kind of problems that we would like to be able to solve this week are problems that look like this. This is an example taken from one of the me time assignments that I set up in Newton Alta. Let me zoom in on a little bit so we can read it better. So in this example, we have a motorcycle which was bought for $10,000. And as soon as you buy a physical asset, it tends to start losing its value, both by virtue of time passing as well as by virtue of its use. And so this motorcycle is such an example. What it's saying here is that this motorcycle is depreciating continuously at 9% per annum. Per annum just means yearly. And they want to know, what is the value of this motorcycle? What is it going to be worth after 7 years? And then they want us to round this answer to the nearest dollar. And this sounds like a very quick question, but I actually want to get a lot of mileage, so to speak, out of this question, because I want to use it as an example to take a step back and figure out why the behavior that's being described here is not well modeled by a linear function, the kinds of functions that we've already spent quite a bit of time studying and coming to grips with. What makes the behavior we're seeing here different from a linear model? And then secondly, I want especially to think about the role that this word continuously is playing in this example. What does it mean for something to depreciate continuously at a certain rate as opposed to depreciate in different fashions? I want to try and be as careful as possible in how we describe this, because there is a very real tendency on the part of students in this material to see a problem like this and instantly start seeing variables that they can plug numbers into in formulas. You pull a formula off the shelf, put it on the page, plug the numbers in, turn the crank, and then hopefully we get an answer. Well, are we getting the right answer? Are we turning the right crank? Are we using the right model? Those are the kinds of questions that are more important to me in this class for all of you to come to grips with than can I navigate the order of operations correctly. So my goal is for us to take apart a problem like this and figure out what are the different ways in which we could understand the way that this motorcycle is depreciating. And then maybe at the end of the day, which is the one that this problem is asking for in the final analysis. So here's how I want to start. Let's actually start and just get some whiteboard space for us here. Let's start by just imagining, just as a numerical matter, right? So we were given this problem. This problem is given to us written in words using the verbal description, right? Let's try and translate this to some numerical data. So I'm not going to reach directly for a formula off the shelf. Instead, I'm just going to take this opportunity to crunch some numbers. And in these numbers, what I want to do is come up with a way of relating the year, the number of years since the purchase, So when this quantity is 0, this would indicate the year in which this motorcycle was purchased. And then on the other hand, I want to be able to say what is the value of the motorcycle in that year. And let's have this measured in thousands of dollars, just so that I have numbers that are a little bit easier to work with. So according to this problem, the motorcycle was purchased for $10,000. And so what that tells me is that in year 0, the value of this motorcycle can be said to be 10. So this one data point here is telling me about the purchase of this motorcycle. Let's give these two quantities, the year and the value of this motorcycle, let's give them names. Let's call the year T. Let's call the value, I don't know, let's call it A. Who knows? It doesn't really matter what we call them. At the end of the day, when we go toward a graphical interpretation of this data, we're probably going to take this number of years since purchase and make this my X variable. And we're probably going to take the value of this motorcycle and make it my Y variable. That's just probably what we're going to do with this data when it comes time to actually putting it onto a Cartesian coordinate system and graphing it to be able to make some predictions. But just so that we can retain some meaningfulness in the variable names that we choose, I'm going to let T represent the year, because T somehow stands for time, and A represent the value of this motorcycle. Maybe A stands for amount of money or something like that. So what this is doing for me right away is it's giving me one data point on my graph. If we switch over to graphs for a minute. When X is 0, Y is 10. So that gives me the first of my data points. And so the next thing I would do is go back to this description one more time and say, what does it mean for the value of this motorcycle to depreciate by 9%? So I want to skip over the word continuously here. And I just want to think about what does it mean, what would it mean to depreciate by 9%? So maybe I can delete this word continuously here real quickly. See if it's going to let me do that. And as usual, streaming from the office makes my computer so slow that it becomes almost unusable to do anything meaningful. Let's see. Nope, it must be down here. It's probably not worth doing if I can't do it in the next few seconds here. Can't get it there. Can't get it there. All right, well, in that case, let's not bother with trying to delete this word. But I am going to skip over it, so I'm not going to pay attention to the word continuously right now. I'm just going to pay attention to what would happen if the value of this motorcycle were to decrease by 9%. And this is something that we talked about last week. Right? Last week we talked about what it would mean to decrease a quantity by a percentage. To decrease by 9%. And remember what I said, this was at the very end of last week's live stream. The best way to think, most efficient way to think about the arithmetic that's involved in decreasing a quantity by a percentage is, instead of focusing on the value that's being lost, focus on the value that is being retained. In other words, if I'm shopping a discount sale at a store, rather than seeing that pair of jeans as 30% off, the easier way for me computationally is to think of it as 70% on, right? That's not what the retailer wants me to think about, because they want me to focus on the money I'm saving. But from the computational perspective, I want to think about the money that I'm keeping, or the money that I'm spending in the case of the discount example. So to decrease by 9% is the same thing as to keep 100% minus 9%. In other words, that would be 91% of the original value. So when I go to investigate, for example, how much would this motorcycle be worth after 1 year of ownership, rather than thinking about that value as being a two-step process of first figuring out what 9% of the value is and then subtracting So multiplying and then subtracting. I've instead done the subtraction part first. I've done it right up here when I subtracted 9% from 100%. And so I do that subtraction in percentages, not in dollars. And then I use that percentage, the 91% of the value that I'm retaining, as my multiplication. And so to keep 91% of my value, I just need to multiply by 91%. So what I'm setting up here is a correlation. A correlation between how the number of years of ownership is changing and how the value of my motorcycle is changing over the course of those years. Sorry, let me get that percentage sign into view here because that's kind of important. So for every 1 year that passes, this motorcycle is going to retain 91% of the previous year's value. Okay. Again, I'm skipping over the word continuously for right now, but we'll get there when we get there. Now, keep in mind, 91%, anytime you see a percent sign, this was the main topic last week as well, anytime you see a percent sign, it's the same as a division by the number 100, a ratio whose denominator is 100. So to turn 91% into a number that I'm capable of dividing or multiplying by, I need to change that percent sign into division by 100. And another way to do that would just be to take 91 divided by 100, which is 0.91, and make that the decimal by which I am going to end up multiplying here. So times 0.91. So let me take this opportunity before we go any further and write down, I'm going to write this down at the bottom of the screen here, what's happening in my data. So for every plus 1 year that passes, the value of this motorcycle is multiplied by 0.91. Right? So that's kind of a crude arithmetic description of what's happened here from year 0 to year 1. The years went up by increase of 1 year, plus 1. And the value is going to go, it turns out, down. And the reason it goes down is it's getting multiplied by this number, 0.91. And that number is less than 1. So when I multiply by it, that quantity gets smaller. So now finally we'll do that multiplication. 10 times 0.91 is 9.1. So after 1 year of ownership, if over that course of that year, the total depreciation in my motorcycle was 9%, at the end of that 1 year period, the value of the motorcycle is now $9.1 thousand, or if you like, $9,100. And so I could put that data point in my chart. And now I've got here my second data point. So here are my 2 data points for what's happening with the value of this motorcycle. Over the course of just the first year of ownership, the value goes from $10,000 when I first purchased it to $9,100 1 year later. Let me go ahead and add axis labels to my graph. Years since purchase on the horizontal axis, and value of motorcycle in thousands of dollars. Whoops, those are dollars. There we go. So just so that we're clear about the practical meaning of this. I lost my axis scale here. Let me fix that real quickly. You nudge your mouse's scroll wheel and everything just goes to... Okay, there we go. So there's 2 of my data points. And with these 2 data points, let's take a moment and let's ask the question which is first on my agenda list for today, which is, what is the difference between exponential behavior, which is what we're talking about this week, and linear behavior, which is the kind of behavior that we talked about for the first half of this unit. What would a linear progression look like in this example? So a linear progression would be the result of fitting a linear equation, y equals mx plus b, to this data. And to get Desmos to do it, remember, we'll tell it that y and x are coming from our lists, and that instead of an equal sign, we want a little twiddle here in the middle. And so now Desmos fits a nice straight line to my data. Let me just make it a dotted line here so we're not going to confuse ourselves too much. And so there would be a linear model. Desmos is also giving us the slope and the intercept of this equation. So let's write those down just for the record. So with these two data points, my linear model, my linear fit, would be y equals minus 0.9 x plus 10. Right? That's the slope and the intercept that I'm getting off of the Desmos output for this straight line. So if that were indeed the right model for this depreciation, then in a linear model, remember, linear models correlate amount changes in both the independent and the dependent quantities, both the x variable and the y variable. And a couple of weeks ago, we spent a lot of time on questions like, what does this number, negative 0.9, mean? What is this number actually telling me? And this number would actually be telling me, right, that for every 1 year that passes, the value of this motorcycle is decreasing. The value decreases. And how much does it decrease by? Not by 10%, as we might be tempted to guess based on that slope, but this negative 0.9 is actually a number of dollars. It's a number of, it's a value of the y quantity, because linear functions deal in amount changes. And so the value decreases by an amount of $0.9,000. So in other words, that's just a different way of understanding what's happening from year 0 to year 1 over here. From year 0 to year 1, this motorcycle has lost 0.9 of its value. $0.9,000 of its value. Right? So in other words, what I'm saying here is that there's two ways of understanding how this quantity is changing from 10 to 9.1. One way is what we get by subtracting 9.1 minus 10. That gives me negative 0.9. And the meaning of that is that the motorcycle is losing $900 of value in that first year. Right? So that's an amount. That's an actual dollar figure. But the other way of understanding what's happening is not by subtracting 9.1 minus 10, but by dividing 9.1 by 10. That's what's going to give me this number over here, 0.91. And that number is contextualized differently. Because it's not a dollar figure, it's not an amount, because it's not the result of subtracting, which is going to keep the units of these the same. It's the result of dividing, and dividing is going to have the effect of canceling those units. So this 0.91 is not $0.91,000. It is a dimensionless figure that tells me how the dollar amount in the first year is being multiplied to give me the dollar amount in the second year. And so that 0.91 means that 91% of my value is being retained from 1 year to the next. And if all I do is I look at the first 2 years, I can't tell whether or not the behavior that I expect here should be linear or should be something not linear, something exponential, as we're going to talk about today. But the key difference is in how we arrive at these two different expressions of change. One of them we get to by subtraction, and it gives us an amount of change. $900 are lost in the first year. The other we arrive at by dividing, and it gives us a ratio. It gives us a percentage of change. A percentage of value that was lost was 9%, because 91% of value was retained over the course of that first year. So in order to figure out why it is that we don't want a linear model, to figure out why the linear model is limiting here, why it's not what we're looking for, let's look 1 more year out. So I want us to find a comparison for what is going to happen with this motorcycle in year number 2. What's going to happen? And that 2 is just 1 more year past year 1. Right, so all I'm doing is I'm adding 1 more to the number of years in my independent variable, my x variable. And so in my chart, in my data table, if you like, I'm just going to have an x value from an x data point, is x value is going to be 2. Now, on the one hand, if we believe the linear model, then the linear model would claim that what has to happen over that year is that this motorcycle has to lose $900 again, okay? Minus 0.9. And if I subtract 0.9 from 9.1, I'm going to get 8.2. So the linear model would predict that the value of this motorcycle at the end of the second year would be $8.2 thousand. Right? I did that right. Yes, there we go, 8.2. And if I were to plot those 3 points on my coordinate axes, those 3 points would all lie on the same straight line. After all, that's why we call linear functions linear in the first place. Their graphs are exactly straight lines drawn in the xy coordinate system. But if I'm following the information that we're given here in this problem, which is that the value of this motorcycle is not decreasing at a consistent amount every year, but it is decreasing at a consistent percentage every year, that would suggest to me that what I really want to do is not subtract 0.9, not decrease the value by $900, but rather what I want to do is multiply by 0.91 again. Lose another 9% of this motorcycle's value. If I do that, then what I end up getting is 9.1 times 0.91. Type that into a calculator. 9.1 times 0.91. 8.281. And so that gives me a number that doesn't agree with what the linear model is predicting. Right? So we're in a situation here where I have sort of two different competing claims for what the value of this motorcycle should be at the end of that second year. If its value is really decreasing in a linear fashion by a constant amount of money every year, then at the end of that second year, $8,200, 8.2 thousand, is going to be its value. On the other hand, if it's decreasing by a percentage, that's a percentage of its value in each individual year. So as the value of the motorcycle goes down, if we're taking the same percentage of that value every year and depreciating by it, then the amount of money by which it depreciates is going to get smaller and smaller every year because the value of the motorcycle is getting smaller and smaller every year. And we're taking the same 9% of it each time. Right? Which is why, if we're following the percent depreciation model, at the end of that second year, its value is more than the linear model would have predicted. $81 more than the linear model would have predicted. And so our goal this week is to study models that are more like this percentage change model. We want to move away from linear models this week and look at models in which, as my independent variable, as my x if you like, as my x increases by amounts, the y variable, the dependent variable, is increasing or decreasing not by amounts but by percentages. Every time we add one more year to x, we're multiplying by 91% in y. So addition is happening in one of my variables, multiplication is happening in the other one of my variables. And those are the kinds of models that we are going to care about this week. So what does that mean for our graph? Let's go back and let's just enlarge this graph to the full screen here, just so we can be seeing it as well as we can. Okay. What does this mean for my graph? Well, it means that, let me turn my dotted line off here. If the value really is 8.281, you can barely see it, but this third data point just got nudged upwards ever so slightly, right? To the point where my correlation coefficient for the linear model is no longer a perfect 100%, right? Because these three points do not lie on the same straight line anymore. Even though it still kind of looks like it, this third data point was moved just enough that it doesn't lie on that straight line anymore. And that trend becomes more apparent if we go out further and further and further. So this question asked us to predict what's going to happen at the end of the 7th year. So what I need to do then is, again, follow this recipe. I'm going to erase the linear prediction for right now so we don't confuse ourselves. I want to follow the recipe of every year multiplying the value of this motorcycle by 0.91, so that in year 2 it's 8.281. In year 3, 8.281 times 0.91, 7.53571. There's going to be its value at the end of the third year. Multiply that by 0.91. We're going to get 6.8575. So I'm doing this very explicitly for now. Of course, the ultimate goal is that we're going to come up with a formula to describe how this is all happening. 6.2403. Multiplied by 0.91 again. 5.6787. And then one more time, multiplied by 0.91. 5.1676. So what to notice about this graph over here is it still at a glance kind of looks like it's a straight line. But if we think about what that original straight line that we had drawn a few minutes ago, the line y equals minus 0.9x plus 10, there's that original straight line that we got when we were assuming that this was linear behavior. And now look at where the data is actually going. It's actually bending. It's bending in a way that makes it lie above that line. Again, because as the value of my motorcycle gets smaller, that 9% that it depreciates every year is getting smaller with it. And so the amount of value the motorcycle loses each year is actually itself getting smaller and smaller. And so the slope of this depreciation is getting more and more gradual over time. And so the value that the depreciation model, the percentage change model, is predicting is going to be higher than the value that the linear, every year you lose $9,000 or $900 approach would have predicted. Right. So the kind of curve that we end up getting here is called an exponential curve. In this example, it's called an exponential decay curve. Decay here meaning that it's a decreasing function, right? As we read this graph going from left to right, the values of the data points, the y values of the data points are going down. So it's still a decreasing function, just like a linear function with a negative slope would be. Right? But the fact that it's exponential, this is the word that communicates that there is a constant percentage change per unit of change in the x variable. Right? So we're changing the y coordinate here, the y value, consistently from a percentage basis, not consistently from an amount basis. So I realize now that I just wrote that down and you didn't see it. Here it is. Right? So we call this kind of behavior an exponential decay. The opposite of exponential decay would be exponential growth. If I have an exponential function that is bending upwards instead of downwards, then we would have an exponential growth function instead of an exponential decay. So my next goal is to come up with an equation that models the behavior that we have going on over here right now. And actually, if you can still see my browser window for a minute, let me make it bigger again. One of the ways we can understand this exponential function is already kind of here in my calculation. So how do I figure out the value of this motorcycle at the end of the 7th year? What have I done in total? I've taken 10, which was its original value in thousands of dollars. I multiplied it by 0.91 once, and then again twice, and then again a third time, and a fourth time, and a fifth time, and a sixth time, and a seventh time. So at the end of the day, here's what I have. 10 times 0.91 times 0.91 times 0.91 times 0.91 times 0.91 times 0.91 times 0.91. So I've multiplied 10 by that same number, that 0.91, that 91% of value that's being retained every year. I've just multiplied by that 0.91 7 successive times. And the abbreviated way to communicate that is that we can use an exponent to do so. And that's why we call this behavior exponential. So here's the idea. Let me get it back on our screen here for a second. So this was 8.281. But how we understood where this 8.281 came from is that it was 10 times 0.91 times 0.91. And another way of writing that is that that would just be 10 times 0.91 to the second power. And again, I'm kind of running off the screen here. Let me put that in a better spot. 10 times 0.91 to the power 2. So that's a more efficient way of writing down what this calculation is that we're doing. Right? And if I were then to want to get what the value was in year 3, I would have to multiply that again by 0.91. And when I multiply it again by 0.91, I'm going to get 10 times 0.91 to the power 3. Right? And that just so happened to be the decimal, what was that? 7.53571. But you can kind of see what's happening here, right? That the number of years, the value of x or t or whatever you like here, is just showing up as exactly the number of times I have to multiply that initial amount of 10, that amount when t is equal to 0. It's the number of times I have to multiply that 10 by 0.91 in order to get the value in the year that I'm looking for. So in year 7, which was the year that's supposed to answer this problem, right? In year 7, the value that I should get is 10 times 0.91 to the 7th power. And indeed, if we evaluate that out, that's what gives me this 5.1676. And so what this suggests to me is it suggests that I can have an equation that relates t with a or x with y, depending on how you like to see this, right? That to get the value of my motorcycle, I just have to take my original amount, which here was $10,000, the purchase price, and just multiply that amount each year that passes by 0.91. So I'll multiply by 0.91, and the number of times I have to multiply by 0.91 is t times the number of years. So this t ends up in an exponent. I want to be real careful here to make that look like an exponent. Right. And there is an equation that can describe the exponential behavior, the exponential phenomenon that we've been modeling up until this point. Right. And so this is a model of depreciation that is the simplest possible model that we can come up with. In fact, it's often called simple depreciation. Or if you're talking about money, it gets called simple interest. Basically, what it means is that 9% that's given to us in the original statement of the problem here, that this 9% is exactly the percentage of value that is lost at the end of each 1 year period. Right? So when I compare my value today to my value 1 year ago, I have lost exactly 9% of that 1 year ago value today. Right? The issue, of course, if I'm working this particular problem in Newton Alta, is that the answer that we got, 5,168, I don't see that answer in the list here. And the reason I don't see that answer in the list is because we've ignored one word in the statement of this problem, the word continuously. And this word continuously causes a lot of heartburn because to really adequately, rigorously understand what it means for something to decrease or increase at a continuous rate really is a question that we need calculus to answer completely, to be completely satisfied with what continuously even means. After all, continuously would have to mean that that this 9% depreciation that's happening is not just happening once every year, like every year on January 1st, suddenly poof, 9% of your value is gone. That's the kind of model that we've already modeled right here. That's what's sort of already happening in my data. But that's not how depreciation typically happens, and it's not how interest accrues on your interest-bearing investments or on your credit card balances or any of that kind of stuff. Interest, when it accrues, and depreciation, when it happens, is always happening. So it's not just 9% happens once every year. It's not just 3% happens once every quarter, which would be sort of, or once every 4 months or something like that, because that would look like 9% over the course of the year, but it's not quite the same. It wouldn't be the same thing as 1% happening 9 times every year. It wouldn't be the same as 0.1% happening 90 times every year. It would be the same thing as taking some infinitely small portion of that 9% and applying that depreciation in every infinitely small interval of time happening throughout the year. And that seems really hard to wrap our heads around, because it really is calculus. Calculus was invented and sort of laid out and fleshed out by people like Gottfried Leibniz and Isaac Newton, specifically to be able to wrestle with questions about continuity and continuously and infinitely small things and infinitely large things. That's what calculus is really good at. So we're not going to rigorously explore what it means, or like how to discover a model for a continuous percentage change at a certain annual rate. But instead, let me put it to you this way. Let me actually go back into our Desmos for an example. And let me start just a brand new graph here for a minute. Because what I'm interested in is, if you, let's think about what the value of this motorcycle would be after just 1 year. So let me write this in here so that we all know what I'm writing here. Note, the value of a $10,000 motorcycle that depreciates at a 9% annual rate, but is compounded, let's say, C times per year. So here's what I mean by that, right? I have my $10,000 motorcycle, right? And at the end of the first year, if we only compound that depreciation once, then its value at the end of that 1 year is $9,100. Right? Maybe for now, let's make these units. Let's make these units actually dollars now, so you can see this is $9,100. So this would be the value. Let me get a blank screen underneath us for a second here. This would be the value if I were to depreciate this motorcycle just once by the 9% amount, just once every year. Like every January 1st, I just swipe 9% of the value of this, but the rest of the year nothing happens. So with 1 compounding throughout the year, the value is going to be $9,100. On the other hand, I could instead choose to take that 9%, that 9% that we're losing, and maybe split it up so that over the course of the year, we're going to lose 3% 3 times, right? So take that 9% and just cut it in thirds, 3% at the end of, so maybe I lose 3% on May 1st, and then I lose 3% again on August 1st, and then I lose 3% again on November 1st, or something, right? So 3 times during the year, we lose 3% of value. So what's that going to look like? Well, instead of 0.91 to the first power, to lose 3% is to retain 97%. So I'll start by taking away 3% once, but then I have to do it 3 times. So when I lose 3% 3 consecutive times, the value now at the end of that is not $9,100, but $9,126. So what that's telling me is that when I have 3 compoundings happening throughout the year, my total value at the end of the year is not going to be $9,100 anymore. Was it 9120? Make sure I'm getting this right here. 9126.73. So it's the same annual rate of depreciation. We're just cutting up that annual rate and compounding it a different number of times in these 2 different schemes. Notice when I do it 3 times over the course of the year, I actually end up with this motorcycle keeping more of its value than if we just depreciated it once over the course of the year. Again, because the more times we compound it, the smaller of a fraction we're pulling from each time. And so the depreciation amount is going to be less. What if instead of cutting it up into thirds, we cut it up into ninths? So every 52 divided by 9, every 6 weeks or so, we'll take away 1% of your motorcycle value. So that 9 times throughout the year, we're going to take 1% each of those 9 times. So that would be 9 compoundings. Let's figure out what the value would be in that case. Every time I take away 1%, the motorcycle is keeping 99%. And I have to do that 9 times throughout the year. If I do that, then with my 9 compoundings over the course of the year, the amount of value that this motorcycle retains is $9,135.17, if the number of compoundings is 9 throughout the course of the year. So that's still a different amount than the previous one that we had, right? But it's not as different as the difference between 1 compounding and 3 compoundings, right? Here the difference is just like $8 or $9, right? It's not as big of a difference as the $26, which is the difference between 1 and 9. So what I want to do is I want to use this, just use my Desmos technology here, to figure out what would happen as I turn this number of compoundings up higher and higher and higher. Okay? Because we're trying to get to a place where we can think of ourselves as compounding this thing constantly, continuously. We take that 9%, we split it up into infinitely many small little intervals of time throughout the year, during which each of them we lose a small, infinitesimally small percent of the value that's going to add up somehow to that 9% annual rate. So let's use this Desmos tool to actually do that modeling. So let's think about what's happening. I'm taking away 9% of my value, but I'm going to cut up that 9% among C different intervals of compounding. And then the number of times that I need to do that compounding over the course of the year is also C. So, for example, when I was doing 9 compoundings, 1% each time because it's 9% divided by 9, but then I had to do that compounding 9 times in order to get back to my 9% annual rate. So this is the fraction that I end up with when I'm compounding C times per year. And now Desmos is going to let me make a little interactive slider here that can let us see what's going to happen to this thing as I crank it up. I'm going to try to crank it up all the way to a situation where I'm compounding it once per day. So when I'm only compounding once per year, I get 9100. This was my original assumption. That's back from our simple interest. If I crank this up from 1 to 3, that gives me my 9126.73. Again, same annual rate of 9%, but now I've compounded it 3 times throughout the year. Crank it up to 9 times throughout the year. That gives me the, I can't quite get it, but the 9135 figure. But notice what happens as I crank this up higher and higher. As the number of times that I cut up my 9% over the course of the year gets bigger, and I compound more often, it turns out that that value at the end of the year ends up kind of settling down upon a number. It looks like about 9139. So if I were to compound that 9% once every day, so cut it up into 365 compounding intervals, and then take 9% divided by 365 every day, at the end of that process, the value of the motorcycle is 9139.21. So let me add that one into our list here. 9139.20, and that's if I compound 365 times. And so what happens is the more that I compound, the less and less that changes the total amount that's getting lost over the course of that year. And so what we would say in calculus is that the continuous compounding is a bit like saying if I could compound this infinitely many times throughout the course of the year, and if I could compound it infinitely many times, what we end up getting here is an amount which is going to be equal to the following thing. It's going to be equal to the result of taking my $10,000 and multiplying it not by 0.91 raised to any particular power, but by 0.91 as the exponent of an expression whose base is this fancy number called e. The whole reason for the existence of the number e in our mathematical discourse, the best reason for it, I think, from an application-oriented perspective, is so that we can model this continuous depreciation behavior. So just to get you acquainted really quickly with e is just a number. It's a number with a messy, nasty decimal expansion, kind of like pi. E is approximately equal to 2.718281 8, 3, etc., etc. So e is some number between 2 and 3. It's a little closer to 3 than it is to 2. But it's just a number, so don't feel like it's some huge mystery. And so if I want to know what the value of this motorcycle is after the first year, if it's been compounded continuously, I should just multiply 10,000 by this number raised to the power 0.91. So let me write that down, and then we'll use a calculator to evaluate it. 10,000 times e to the power 0.91. And if you're typing this into a web browser like Google to serve as your calculator, e to the 0.91 you can write in a browser as exp parentheses 0.91. So that's what I'm going to do here real quick, just because I'm using a browser today as my calculator. So 10,000 times exp parentheses 0.91. Whoops, nope, it looks like I messed that up. My apologies. Rewind the tape just a few minutes. Yeah, because I messed this up real quickly. So it's not e to the 0.91, actually, that we end up multiplying by. My mistake. The number that ends up here is actually e to the minus 0.09. So to take away 9% of the value, sorry, you can't see me writing. Let me switch back. The number that I actually want is e to the power minus 0.09. That's what I get for eliding the calculus details, is that I'm not able to catch my own mistake there. Minus 0.09. And so that's what I end up needing to evaluate, which again, if I'm using a browser or something text-based as my calculation tool, I'll just write 10,000 times exp, parentheses, negative 0.09. And sure enough, that number, 9139.31, that number is the continuously compounded loss, the value of this motorcycle at the end of that 1 year, if that 9% annual depreciation rate is compounded continuously throughout that year. 10,000 times e to the minus 0.09. That minus 0.09 here coming from that 9%, 0.09, depreciation, 9% decrease, negative 0.09. So what this does for me is it allows me to say the following. I'm going to jump back to our previous screen here. So when we were taking a simple depreciation or a simple interest type of model to model what's going on in this example, every year we were multiplying by 0.91. And so in that exponential expression, we would call 0.91 the base of that expression. Base is 0.91. And so for a simple depreciation model that loses 9% once a year, one compounding, 0.91 ends up being the base. But for a continuous model, according to what we said on the previous screen, the base of this exponential, rather than being 0.91, it's going to be e raised to the minus 0.09. And so this new base is e to the minus 0.09. And now we get an equation, finally, now that we're almost 50 minutes into today's live stream, now we get an equation that you probably recognize as being one of the equation forms that is frequently used to model any kind of interest, depreciation, appreciation, present value, future value, all of these situations where the value of money or the value of something is changing consistently at a consistent, constant, annualized percentage rate, but that rate is being compounded continuously over the course of each year. So there's the equation that this question intended for us to use. And so rather than the end of my 7th year being 0.91 to the power 7 times my 10, what I wanted instead was e to the minus 0.09 times 7. And when I evaluate that out, again, I'm going to use my browser as a calculator here. 10 times e to the minus 0.09 times 7. Here I'm going to get 5.326. So $5,326. And now that I have compounded this value continuously, rather than on a discrete basis of once per year, now I actually got an answer that is one of the answer choices on this list. And if I submit that, pretty sure that we should have that. Yes, it's right. And again, the way that the guidance that they give you for doing this problem is they give you this formula, v equals pe to the minus rt, and you're just plugging in 0.09 for r, 7 for t, and 10,000 for p. So that's what, if you're whizzing through this work and just getting it done, that's what they were expecting for you to do. But what I'm hoping is that the time that we took here to go over where that formula came from just sort of helps to understand what's going on when a quantity is changing with a consistent percentage change rather than a consistent amount change. Now we get functions that are no longer linear, but which are exponential. And so before we take a short break, we're going to take a break and then come back and talk about how to use the formulas in exponential models to both evaluate exponential functions, but then also solve for values of exponential functions. Let's get on the page just the main differences that we have between the linear and exponential forms in terms of algebra. And then after our break, we're going to talk about the ways to use those exponential models. So what do I want us to come away with here? So on the one hand, we have linear models. On the other hand, we have exponential models. And on the linear side of the house, the most important quantity that we study in a linear model is called the slope. And the slope of a linear model is the thing which is constant, because what it says is each amount change, let me set that in a separate color here, each amount change in one of my quantities, let's say x, has a consistent amount change in y. Right? So as the number of years gets added 1, or you add 2 to the number of years, then you add a certain amount to the value of your investment, or you subtract a certain amount from the value of your motorcycle, right? That we're pairing addition and subtraction operations are what we use to change x and y, right? And we can see that in the formula for how we computed a slope. My formula had a difference in the y variables and a difference in the x variables that powered the whole formula, right? Y2 minus y1 over x2 minus x1, right? So the fact that we're using subtraction here means that we're measuring amount changes in x and y when we're finding the slope. And then the equation that we end up getting, or our equation template, if you like, for any linear model, is y equals mx plus b. Right? So that's what we spent the first half of this unit talking about. But meanwhile, on the exponential side, in place of where we used to have a slope, now we have this concept called a base. And the way to interpret what a base tells me is to say that each amount change in my x variable, so we're going to still think of the what's happening to the x variable as happening via addition and subtraction. The difference is in how the y variable responds. The y variable has a consistent percent change And that is what distinguishes exponential behavior from linear behavior. And so while I still use addition and subtraction to talk about how the x's change, I'm going to use multiplication and division to make all of my changes in the y variable. Right? And the equation model that I can use to represent an exponential function looks like y equals. So I can have a base here, e raised to the power of r, let's say. So I'm going to think of this e to the r here as being my base. And then in the front of it, I'm going to put a number here, call it a, and then I'm going to put my variable x kind of here. So every exponential equation can be written in a way that looks like this. A times e to the r raised to the power x, where the role of this e to the r here is this number is the base. This is the thing that I multiply my quantity by every time x increases by 1. So just to get that verbal description down here on the page. Whenever x increases by 1, adding 1, right? Y changes via multiplication by that base. Right? So when that base was 0.91, right, every time we added 1 to x, we multiplied y by 0.91. When that base was e to the minus 0.09, every time x increases by 1, y gets multiplied by e to the minus 0.09. So that ends up being called the base. And then meanwhile, there's one more parameter in here that we can talk about, and that's the a that's sitting out in the front. In our motorcycle example, the role of a was being played by $10,000. That was the value of this motorcycle when it was first purchased. Well, it was first purchased when x was equal to 0. And so this actually plays the same role as b played in the linear equation. It's the y-intercept. It's the value of y when x is equal to 0. So just as a linear equation has a slope and a y-intercept, an exponential equation has a base and a y-intercept. But because of the difference in the arithmetic, the form of the equations is different. Where linear equations have addition, exponential equations have multiplication. And where a linear equation has multiplication, an exponential equation has an exponent. So that's arithmetically the main difference between the two of these that allow them to model different kinds of behavior. So what I want to do is just take a short 30-second break for us all to catch our breath, especially me. If you're watching this live and are one of my students and have a question via Slack, please drop that into the doctor's office channel for me to see it. If you're watching this via Twitch, feel free to drop questions into the Twitch chat. And at the end of our 30 seconds, I want to come back and look at how to actually use these equations to evaluate them and then use logarithms to solve them. So let's come back in just 30 seconds and we'll move to that last stage. All right, so now we know that the game is different with exponential functions compared to linear functions. It's different because the underlying arithmetic that describes the consistency of the relationship between two variables x and y, the arithmetic is different. For exponential functions, we have addition and subtraction happening to the x variables, but multiplication and division happening to the y variables. And because the arithmetic is different, the algebra is different. And because the algebra is different, we need to develop some new tools to figure out how to do algebra with exponential equations and exponential functions. So I want to look at that from two different perspectives. One of them in which we use an exponential model, an exponential equation, to evaluate an exponential function. What that's going to do is let me take an x that I know and produce a y that I don't know. And then secondly, we need to go the opposite way. If I know the y that I'm looking for, but I don't know the x, how do we go backwards? How do we use algebra to go both of those same directions? So let's start by picking one more example out of our Newton-Alta work for this week. And I want to get a little bit more mileage out of this example than the example might ask for in the beginning. So say we're managing a church parish, and the population is growing with an annual percentage rate that's being compounded continuously. And it says the population grows by 10%, reaches 1.1 times its previous size, every 2 years. And they give us that this is represented by the following formula. Right? So here we're vaulting all the way over the work that we needed to do in our last example and just going straight to the algebraic model. F of t equals p times e to the 0.0477t. And then they tell us the parish just started with 570 patrons. Presumably just started means we can take that number to be our year 0 population. And the question they're asking is how many patrons will there be 10 years on? Right? So let's take a step back from this and figure out what information that we've just been given. We've been given an algebraic model, okay, for this behavior. We've been given a function, f of t. So let's get that written down up here. F of t equals p times e to the 0.0477 t. And here, let's write down, this is a good practice by the way, let's write down the meaning of all of our quantities. F of t is the number of parishioners. T is the number of years since the parish was started. And then P here, well, what would that P stand for? As we were talking about just before the break, that P is nothing more than the value of this function when the value of t is equal to 0. T is equal to 0 exactly when the parish was first started. And so this P would be the population at start. It's the y-intercept of this exponential function. And so based on the information that we have here, the population of this parish at the beginning was 570. Right? They gave that to us as part of the setup of this problem. So we know, therefore, that we can use 570 to represent the starting population, represent the value of p in this algebraic model. So let's just put that right in. And that gives me an equation now, f of t, a function. F of t equals 570 times e to the 0.0477t. And you might ask yourself, well, where did we use the information that they gave us about the fact that the population reaches 1.1 times its previous size in 2 years? Well, we didn't have to use that information. That was the information that the authors of this problem used to discover the formula, f of t equals p to the 0.477t. Right? So we didn't have to put those parameters in anywhere. Those just determined this number, 0.0477. Okay? However it is that happens, and you can maybe figure out how it was that they arrived at that number. Okay, so this is our equation. Now this is our function. Let's look at a graph of this function. I'm just going to open up a blank graph in our Desmos graphing calculator. F of t equals 570 times e to the power 0.0477t. If I type that in and I zoom to a reasonable viewing window here, so maybe I'll go and then 570, so maybe I'll go negative 100 to 2100 or something like that, or maybe just 1500, 1600. I want to be able to see enough of this graph as to make it meaningful. Let me label my axes. So this is years since start, which we call t, and then the vertical axis is number of parishioners, ft. Okay. So here is our graph that's depicting the behavior that we are looking to investigate. And the question has asked us to come up with an estimate of how many parishioners that there will be in 10 years. So 10 years from the beginning, 10 years from the start. So according to this graph, that's going to happen right here when x, the value of x, or t, on my axis there, is equal to 10. So if I were to put a point right there, its x-coordinate would be 10, and its y-coordinate would be f of 10. Okay, so this point right there is going to show me the population after that many years. And when the graphing calculator does the calculation, it comes up with the number 918.403. So we would expect, rounding to the nearest person, that is 918 people. Let's submit that answer. And it's totally fine with that. Okay. But let's go back and actually do the evaluation one step at a time, just to get familiar with how to evaluate an exponential function. So what did I do? What would I have needed to do here? I need to know how many parishioners there will be 10 years after the beginning. And that means that 10 is going to be a value for t in this example. So the population at the 10-year mark, at 10 years, is going to equal, f of 10, which is 570 times e to the 0.0477 times 10. Right? So that's the arithmetic that I need to do. Now, how do I do it? Well, according to the order of operations, I should be looking at exponents before I look at multiplication, and so I don't want to do this multiplication by 570 first. I want to do it after I evaluate the exponential, e to the 0.0477 times 10. But by the same order of operations, the multiplication by 10 that's happening up here has to happen first, because implicitly it's being grouped together with that 0.0477 in front of it with some hidden parentheses, if you like. So we'll do that evaluation first, 0.0477 times 10. That's going to give me 0.477. And then my job is going to be to take e and raise it to that power, which again, you can pull out a graphing calculator, or you can pull out a web browser or whatever. Maybe this time I will use a graphing calculator just for kicks. So on my particular graphing calculator, the button for the exponential is actually the same as the button that has an ln on it. See it right there at the end of my finger? So what I would need to do is press e to the, and on my calculator it actually shows up as e with a little blank exponent up there, and then type 0.477. 477. And I enter that in, and I get a decimal that looks like this, 1.6112. Right? So the value of that, 1.6112, is approximately some decimal 1.6112. And then the only thing left for me to do would be to multiply that number by 570. Multiply that number by 570, and that's where we get the number that we just typed in here, 918.4. Right? So using an exponential function, when I know the value for x and I don't know the value for y, right, is just a matter of following the order of operations. And so that's, in this particular example, how I can figure out that after 10 years, I have 918.4 people in my parish. So that's the simpler direction. The more interesting direction, the more complex direction to navigate, is how do we go the opposite way? Let's suppose I ask a backward question. How many years will it take for this parish to grow to 1,200 members? So that's the question that I want to investigate now. And we're going to investigate this question just first graphically. Right? But then after we've investigated it graphically, we want to look at the algebra. How can we, if I know a value for y in an exponential function, how do I discover the corresponding value for x? So in this example, we know we want to find a situation where there's 1,200 members. And so we know that 1,200 is going to be a value on my y-axis. It's a number of parishioners, right? And so what I'm going to do is take the liberty here of sketching in a horizontal line, y equals 1,200, right? Here is my 1,200 parishioners line, right? Because on the y-axis, this is the point 0, 1,200. And so the point at which I have 1,200 parishioners is going to be the point where my exponential growth curve here, where this equation intersects with my 1,200 parishioners equation. And again, my Desmos graphing calculator can ride in on a white horse and tell me that the value of t for which this happens is about 15.607. So zooming back out for a second, we could say something like, I think that's what I wanted to do. Yeah, there we go. So 15 years, or 15.6 years after the beginning of this parish, we can expect that the number of parishioners will be 1,200. Right? So that's graphically an approximate solution to this. If you have a graphing calculator, this is a good way to do it. We also want to figure out how to do this with algebra. So how can I not use an exponential equation to evaluate a value, but how to solve an exponential equation to discover an unknown value? And so that's how we're going to culminate today's live stream, is by looking at that question. So let's put our numerical solution that we found here on the side for a moment and figure out how to do it with algebra. Get our numbers back on the screen here. Okay, so how would I have done this with algebra? Well, first of all, we'll recognize what the question is. The question is, when the number of parishioners, that's f of t, is 1,200, the question's asking, what is t? In other words, how many years would it have taken to reach that level, right? Or on my graph, when the value of y is 1,200, what is the value of x going to be? Right? So what I can do is I can evaluate, I can substitute in my equation 1,200 for f of t. And I get now 1,200 equals 570 times e to the 0.0477 t. Let me nudge my graph off to the side a little bit here, because as usual I'm drawing over myself. Don't want to do that. Here we go. Okay, so what I have is an equation that I now want to figure out how to solve. How do I get this equation to have t by itself? Solve for t. And what makes this equation look intimidating, and why we need some algebra that we haven't talked about yet in order to solve it, is that location of my t is trapped up in the exponent next to this coefficient 0.0477, right? And so we have to go on a rescue mission to get this t rescued from this exponent in order to figure out what its value is. That's the bad news. The good news is that we understand the order of operations well enough, particularly having just done the last example that we did, to know how the expression on this right-hand side has been put together. Let's imagine that I'm t for a moment. What's the first thing that's happening to me as t? Well, the first thing that's happening to me according to the order of operations is I'm getting multiplied by 0.0477. So let's think of that as the first layer of wrapping paper that surrounds my t. It's multiplication by 0.477. Multiplication by 0.0477. That's the first thing that's happening to t. The second thing that's happening to t is that it is becoming the exponent of an exponential expression whose base is e. And so the next layer of wrapping paper is that e is being raised to that value. E raised to that value. So e to the that, I'm going to call it. Okay? That's the next layer of wrapping paper. And then finally, the very last layer of wrapping paper, the very last thing that's happening to this quantity, is it's getting multiplied by 570. So the outermost layer of wrapping paper is that multiplication. So the order of operations tells me how this package was wrapped. And if I have to solve this equation to get the t by itself, the burden there is that we unwrap this package. If I want to get the t by itself, I have to unwrap this package. And to unwrap it, we have to unwrap each one of these layers of wrapping paper. But we have to do it in the opposite order in which the package was wrapped in the first place. So the very last thing that the order of operations does is the very first thing that we need to undo if we're going to solve this equation. So let's start that process. The first thing I should undo is the last thing the order of operations did do, which is multiplication by 570. So the first thing I want to do is undo that multiplication by 570 by dividing. Remember, apply the opposite operation and do it to both sides of the equation. Deal with that first. And if I do that, this 570 is going to no longer be there on the right-hand side, and we will have e to the power 0.0477 times t. That gets us one step closer to where we want to be. And on the right-hand side, I'm going to write 1200 divided by 570. I'm not going to simplify that for right now. Let's wait. We'll simplify that in a little bit. So I've now unwrapped my outermost layer of wrapping paper, this multiplication by 570. The next layer I need to unwrap is the exponentiation, the fact of raising e to a quantity. What I need is something that can undo that. And this is as much as I'm going to say about the definition of logarithm. But the logarithm, its purpose in life, is to undo an exponentiation. So logarithm equals a reverse exponentiation. Reverses exponentiation. It rescues the exponent. Right? It takes this 0.0477t, which is trapped up in the exponent, and it rescues it down to the base. In other words, it just cancels out that base of e. And the particular kind of logarithm that accomplishes this is called the base e logarithm. Or the name by which we generally know it is the natural logarithm, ln. So ln is the name of the operation which undoes an exponential whose base is equal to e. And so what I get on the right side of my equation is just the exponent that we had from before. On the left side of the equation, what I get is ln applied to this number, 1200 over 570. Right? And this is the step that's new. This is the piece of algebra that we haven't talked about how to do yet, okay, until just today. Every other step that we're using in the solution of this equation is something that we've seen in one fashion or another before, right? Because it just had to do with addition, subtraction, multiplication, and division of the kind that we had to know how to navigate even to solve linear equations. So this one step that we did here, to take a natural log to cancel out the base of e exponential, that's the only thing that's new. And in particular, what that tells me is that I know now what the last step in my solution is. I need to undo this last layer of wrapping paper, which is multiplication by 0.0477 by dividing by 0.0477. And at the end of the day, I'm going to go to the upper right-hand corner here of the screen. At the end of the day, what I have is I have my t standing alone, and its value is the natural log of 1200 over 570. 1200 over 570, all divided by 0.0477. Sorry about covering myself up yet again. There we go. So I know now how to get that t by itself. The only thing that's left to do is just to get a number out of this jumble, for which, again, let me just use the browser window to type this in this time. So what did I have? The natural log of 1200 divided by 570, and then I divided that by 0.0477. And sure enough, I do that operation, and I get 15.6067, etc., etc. And that does indeed answer the question. According to Desmos, it lines up with what was gotten on the graph here. How many years will it take for this parish to grow to 1,200 members? About 15.6 years. Logarithms are classically confusing. Students of algebra have been stubbing their toes on logarithms since time immemorial. And one of the reasons I think that that's the case is that logarithms are much simpler than most algebra textbooks make them out to be. If you only think of a logarithm as something to do to get rid of an exponential, to rescue a quantity from the exponent of an exponential expression down to the base, where we can solve for a variable that's trapped within. If you only think about a logarithm as a way of doing that, that should be enough to get you through. Now, logarithms have a whole slew of interesting algebraic properties that we can use to do other stuff. Those are properties that I don't care so much about for the purposes of this class. If you only know that a logarithm is the tool to use to rescue the exponent out of an exponential expression, where the natural logarithm is for base e, which all of our bases will be e, I believe, in this chapter, that should carry you through. But if you do have more questions on how to use logs for some of the problems in our homework, or if you're working on quizzes or exams, do drop those questions if you're one of my current students into one of our Slack channels, Doctor's Office channel, or the Math channel, depending on how wide is the audience for your question, and I'm going to be happy to help you out with this. This is the most strenuous algebra that we are going to have the opportunity to do all semester. So if it's tricky, if it's frustrating, there's a good reason for that, and you're definitely not alone. So please do reach out to the other members of your group, as well as to me, as well as to the rest of the class via Slack, if we can support you in solving some of these problems. So as we go forward into next week, we're going to go into exam number 2, which is going to cover our algebra unit. So I'll be in contact with you to give you updates on your quiz progress and your grades up until that point. And then exam 2 will be made available next week, so you can begin working on that and do at the end of the week. So next week's live stream, just like on the last exam that we did, will be an exam review live stream, and we'll go forward from there. I look forward to working on it more with you, and I'll see you then.